Hello and welcome. This week we are going to start really diving into semiconductors. Diodes are going to be front and center as we go through our lab. And I also really want to start looking at computer controlled systems. How do these systems work? What's the mindset behind the engineering that goes into these systems? Understanding just a couple ways about how computers really view the world in a really basic sense will help us to understand how circuits are wired up and give us a better idea of how to have some expectation when we're looking at wiring diagrams and a little intuition. So in this first little block diagram that we have here, the center is my computer. So this would be the module inside the vehicle. We have inputs that come in from sensors, so temperature sensors, speed sensors, position sensors, and the one that everybody tends to forget are switches. A simple switch is a sensor. If I want to roll the window down, the first thing I'm going to do is push a switch. If I want the headlights to turn on, the first thing I'm going to do is turn a switch. If I want my vehicle to start up, I'm either going to turn a key, which is a switch, or push the little stop-start button on my dashboard and my vehicle will start up. So switches are probably the most common input that are used, especially in body electrical for sure. And then we have our outputs, and the outputs this is where we start to get into the electrical side of the circuit. A lot of this is electronic, so really low current flows. We're not really trying to make anything happen. We're just trying to switch the voltage that's being monitored inside the module so that it can look at its programming and decide what output should be performed. Let's say that I am driving down the road and the module starts to get a vehicle speed signal that says we've reached 5 miles per hour now. On a lot of modern vehicles, the doors will lock, and that's the computer monitoring an input vehicle speed, paying attention to its programming, and then making a decision based off of that programming. Everything up to that 5 miles per hour, the car didn't care. It was like, okay, it's great that you're at 5 miles per hour. In this case, let's call it like a body control module that's monitoring this. Okay, I don't really care that I'm at 3 miles per hour right now. At 5 miles per hour, all of a sudden it gets excited, and one looks to see if the doors are locked, and if they aren't, it locks the doors. After 5 miles an hour at 6, all of a sudden it doesn't care anymore. At this point, the vehicle's moving down the road. We've passed that threshold at which the car should have locked the doors all by itself. And so now it can spend its little computer time focusing on other things. So we've got inputs, sensors, we've got our actual computer itself, and then we have the output, which is the power window motor, the door lock, the starter motor, the fuel injector. I think you get the point. On the top here, I've got an electrical circuit. So circuit protection from my power source, circuit control, and then I actually have the loads here at the end. Down at the bottom, I have an electronic circuit, and this electronic circuit really starts to change the way that we think about electricity in cars. So at the top, these switches are circuit control. If I push that switch, the motor will spin, the light will glow, the heater will warm up, the solenoid will create magnetism and open and close something. But it's all dependent on this switch right here. This is the only thing that can either turn it on or turn it off. And this diagram's drawn and it's at rest position because the motor's not always going to be spinning for my power window. So when the diagram's drawn, it's showing normally the switch is in the off position. So we've covered a couple of bases there. On my electronic circuit, at the bottom, my switches are inputs. They're mere requests that something is allowed to happen. If I turn on my headlights on my car, I've got auto headlamps, so I can switch to auto headlamps. That doesn't mean that my headlights are going to turn on or turn on as brightly as they would if it was dark outside. Often vehicles have daytime running lights, so they just have like a dim light that is shining all the time to increase some visibility. But I turn that switch on and the vehicle, the module, more specifically, pays attention to a few things. One, it's limited by the way that the circuit board is stamped and the components that are built into it. You can think of this like the skeleton. So this is just the plain circuit engineering that's built into that little computer board. The next thing it looks at is its read-only memory. This is it works a little bit hand in hand with the way that the board is actually structured and the chips, the little processors that are built into it. The read-only memory can't be changed between the structure and the read-only memory. This is the main reason why a powertrain control module is a powertrain control module only, and a body control module is just a body control module. You can't say, oh, my PCM went bad, I'm going to take my body control module, plug the connectors into that one, and then all of a sudden, if I just reprogram it, then I can use it to run my engine and my transmission. No. It's limited by the structure, and those are a couple of those parts. So the actual circuit board and the read-only memory. Next, we've got programmable read-only memory. It's referred to as PROM, and that programmable read-only memory is what we do when we update the software version on our cell phones or on our computers. There are little bug fixes in the programming that they've come along with, or maybe they're adding new features to a vehicle. Owners of Teslas, it's amazing how long ago this seems now, but it was about 3 years ago. In the fall, owners of Tesla Model S's, the cars would update themselves off of Wi-Fi. So if you parked it close enough to your house and it can get the Wi-Fi signal, the car would just update itself like a cell phone would. Maybe when you park it, it says, hey, there's an update. Would you like to perform this update or schedule an update? Whatever. And the next morning, the customer comes out and gets a licensing agreement, terms of use, saying, we just did this update. Congratulations, your Tesla is the best thing that ever existed. Oh, and by the way, we added autopilot to your car. Yeah, I know it's 2.5 years old and it didn't come with autopilot, but it had all the stuff it needed. We just didn't have the software up to the level it needed to be yet. And we got the bugs all worked out, so congratulations, you now have a car with autopilot. So this is programmable read-only memory that's allowed this to happen. We can change that program, and all the computers are still going to be the airbag module, the driver's door module, the body module, the lighting module. It's all the same, but now it's been given some new rules in which to abide by. Then the next thing that we see is I've got 2 electronic control units here, and I got a wire that is connecting them, and it says MPX communication line. So that's multiplex communication line, and multiplexing, we'll get into this in depth later on, but multiplexing is my communication network, and all that multiplexing means is that multiple packets of information can be sent at the same time, because there's not just one wire connecting one module to another in most vehicles. There's usually 2 wires that are connecting anywhere from 2 modules all the way up to, I think the maximum right now for most manufacturers is somewhere around 14 or 15 modules on a single communication network. 2 wires, and all these modules are having a conversation at the same time. And that's the main reason why there's a limit, because if we get enough of us in the same room, which I know there's all these rules out there in laws saying that we're not even allowed to get 10 people in the same room together because of the whole virus situation. But let's say things are normal and we get 15 people in a room, it starts to become very complicated to have a conversation with just one of those individuals. If there's one person in charge and everyone's just sitting there quietly listening, then all that information can go out and it's just a one-way system. But as soon as we start communication back and forth and between different modules at the same time, it gets fairly busy, and so the communication network can only handle so much. But this makes it so that if I hit well, let's use the example, I come up to my car and go to open the door. So when you open up the door on many modern vehicles, there are a few things that happen. One, the interior lights turn on so that you can see what's going on. Oftentimes the exterior lights of the vehicle will turn on as well to give you some visibility around the vehicle Say you're trying to get stuff into or out of the vehicle, trying to not step in a big mud puddle. The fuel pump will prime so that when we go to crank the engine over, it's already provided with enough fuel pressure at the fuel rail to fire off those injectors nicely, and we're ready to go, no delay whatsoever. Computers are woken up, all kinds of crazy stuff goes on. So this is the point between having one computer being able to talk to others, because think about how many computers are in play there. If I open up the door and I just want my fuel pump to prime, a lot of times now there's your driver's door module picks up the signal that the door is ajar, and it sends information to a body control module that then is able to talk to the powertrain control module that controls the fuel pump control module that primes the fuel system. So this makes it, one, sound really complicated and confusing, and there's definitely a point of that's true. But two, it gives us the ability to make all of those things happening without having to have a single wire running from my door ajar switch to the interior light, the powertrain control module, maybe a fuel pump, maybe all the modules need to see some sort of a voltage change that tells them that the door is open. You see, these wiring harnesses would become absolutely ridiculous in size if we continued to add features to vehicles at the rate that we are currently. It's gotten so crazy that for manufacturers like Mercedes, they've started to use the coax cable, basically like our Ethernet cables, fiber optics, and they're using light to send these signals because they need to increase the capacity of these circuits, just because, think about it, it's a luxury car, so there are lots of features that are added to that. So I get an input in one module, and that module's output is sending a little love note to another module, which is the input to that module, that then outputs the motor spinning, the light shining, the heater heating, the solenoiding, right? So, okay, this is the end of me talking about computers like this for a little bit of time. We're going to start getting into the semiconductor stuff now. So inside the computer, we've got these printed circuit boards. These are our chips, little processors, and these are structured a certain way, and we're going to play with a 555 timer at the very end of the electrical section of this class. So you'll get to get an idea of what I'm talking about. Then we've got resistors, which we've already played with. Here's a diode, a couple of transistors, which we haven't gotten to those yet, and we're about to talk about diodes, some capacitors. So we'll get to play with all this kind of fun stuff. Just another look at the same thing. Here's my programmable read-only memory. So that's the one I can change when I do a software update. The CPU would have the ROM inside of it. And there's one last thing that I hadn't talked about yet, which is the random access memory, or RAM. Random access memory is your clock remembering what time it is, even though you turned it off because you left the car. It's the radio station presets staying the same, and it's the adaptive fuel tables and adaptive shift strategy inside the transmission or the engine processor that allows for improvements in shift feel based off the way we're driving. It allows the engine to adjust and adapt for the fact that as it ages, some of the components start to wear a little bit, and that changes some of the performance, and we can adapt to that stuff. It's also the way that we can preset memory seats. So you push the button when you get in after your wife's been driving, or your girlfriend, or whatever, and instead of being tucked up tight, now it's put the seat back just the way that you like it, so that you don't have to fidget around with all the switches and position while you're trying to drive down the road. All of these parts that we were just looking at are made out of semiconductors. So a semiconductor, if you remember, is an atom that has 4 electrons in its valence ring, which is the most outer orbit of that atom. And if we look here, we've got all these atoms lined up in what's called a lattice, because it looks like lattice work, and they're sharing electrons in their stable state. So the most we can hold as far as electrons go in this outer ring is 8. And if you count here, 1, 2, 3, 4, 5, 6, 7, 8. But this atom is sharing these 8 with, here a couple are being shared with this one, a couple with this atom, a couple with this one, a couple with this one. So no one atom at any time has all 8 electrons, but no atom at any time has less than 8 electrons. And this is a very, very stable state. This is what makes the semiconductor the semi part of being a conductor. This would be a really, really good insulator in this state. If we remember, insulators have more electrons in that outer ring, 8 being the most. So this is about as good of an insulator as possible. The way that we make one of these semiconductors work for us, this is silicon that's being shown here, the Si there, it says it at the bottom, is we dope the semiconductor material. So when we're going to make 2 different types of material, N-type and P-type, and a electrical engineer would slap the heck out of me if they heard me saying that N-type resides on the negative side of the circuit and P-type should reside on the positive side. We're not going to consider N being negatively charged or P being positively charged, but if you look at it with rose-colored glasses, or in layman's terms, then really that's the easiest way to understand this. We're not going to go into the physical science. There's no crazy math equations or formulas that are going to get used here. So, long story short, our N-type material we dope with phosphorus, and phosphorus has 5 electrons in its valence ring. So phosphorus is a bit of an insulator. The interesting thing about this is because the maximum number of electrons that any one atom can have in that outer ring is 8, if I've got phosphorus surrounded by a bunch of silicons, and the silicons are all trying to share with each other like nice little semiconductors are often want to do, then what ends up happening is there's one electron that's often misplaced or free, as what's shown in this diagram here. So that doesn't mean that this N-type semiconductor material is going to flow electricity all by itself. It's not. It's still an insulator at this state because we're sharing all of these electrons in the outer rings. Those free electrons are floating around like the tiniest little bits of static electricity you ever thought of. So they're not really going to do anything, but this sets the stage for us to be able to harness the power of these semiconductors and the way that they like to line up and share with one another like nice little semiconductors. So N-type has an extra electron, and there it is in another view. I'm so lonely, I have nowhere to go. And then eventually gets sucked up by one of the atoms and another electron gets spit out for a second. Now I'm lonely, I have nowhere to go. So then the next type, when we only have 2 types of semiconductor materials that we'll be dealing with, is the P-type. So we had N-type has an extra electron. Well, P-type is doped with boron, and boron is a conductor. Boron has only 3 electrons in that outer ring, and so when a boron atom is surrounded by a bunch of silicon atoms, what we end up having is a shortage of electrons. Boron only had 3 to bring to the party, where everybody else was bringing 4. So one atom every once in a while is going to have 1 less electron than it could in its most stable state, and nature's looking for that stability and balance. So having this doped situation where my N-type has an extra electron, my P-type is missing an electron, well, you can kind of see the Romeo and Juliet story that's about to take place. And there we are. We're just seeing in the lattice that we're missing an electron. And they call that holes. Okay? So N-type has an extra electron, and P-type has a hole, a slot in which that electron could fit if we get things oriented the right way. There is our diagram for a diode. The arrow points in the direction that current should flow, and the arrow is pointing with our conventional current flow theory. So it wasn't up until the point that we made atomic microscopes that anyone understood for real and could prove for real that electrons were the negatively charged particles and they were the ones that were flowing and blah blah blah. Up until I think that was like the 60s or 70s. Up until that point, there was no proof of it, and all of the industries had gone along with what Ben Franklin. Think back to 150 when Ben Franklin rubbed his wax and his wool together and made a static electricity spark, just like we've all done with a pillow, or not a pillow, with a balloon when we were little kids at nighttime after a birthday party or something, laying in bed rubbing a balloon on your shirt, watching all the static electricity happen. That's all Ben Franklin was doing. Think about it. He didn't have TV back then, so he had to occupy himself other ways. So, long story short, the diode points in the direction that current is allowed to flow, and it follows our conventional current flow theory that we're using for everything else in this course and for all of automotive for the foreseeable future. In cars, oftentimes you'll see some of these diodes in the fuse panel. They're often related with circuits like the starting motor, the AC compressor clutch, which is a big electromagnet, and they're there to block the flyback voltage that happens when we turn those components off. Because just like our ignition coil, if we make a huge amount of electromagnetism, when we shut it off and that magnetism falls across the coil, a high voltage, thousands of volts, is created and wants to flow in the opposite direction, which means back up towards the switch or the computer that was controlling it. So that diode's there to say, you're not going to get up here and fry this module out. And another look at the same idea, we're using diodes that look like this one, where the stripe is on the cathode side. So this can be spelled with a K or a C depending on whether it's British or English or German or whatever. But the stripe is on the ground side, the negative side of my diode, and that would be what we call forward biased. So when it's forward biased, it's going to allow current to flow through it once I apply the right amount of voltage to it. When it's reverse biased and flipped around, so my cathode would be on the positive side, that's when it stops things from flowing. So that's what I just said. So here we have the deepest I'm really going to get into the chemistry and physical science of this. There's a video that I've linked you to as well in the lab that I recommend you watch. It's kind of weird and a little bit dry, but I do think it's really interesting, and the visuals they have made all this stuff make sense to me years ago when I started teaching this, and I think that for many of you it'll be helpful because we're not able to do as much of the hands-on as we like to, so as much visual stuff as possible I think helps all of us. So here is my diode, my P-type material, my N-type, and so if this was forward biased, I would have my battery positive here and my battery negative or ground over here. And between these two materials, because they're physically different at this point, this has some extra boron in it, this has some phosphorus inside of it. So in these, between these two types of material, what we end up seeing is that I think I actually got that backwards with boron and phosphorus, but who really cares? But in between these two, there's obviously a junction, basically a border in which one type material stops, the other one begins. This junction is what we have to get across to be able to start flowing current. You can see the Romeos and Juliets here want to be together. I've got a spot for you. I got a thing for that spot. Why are we not just flowing electron already? It's because of this junction, sometimes called the margin as well. It takes a certain amount of force, of voltage, to be able to start flowing current across to make the holes in the free electrons come together. And as soon as that starts, it's like someone opened up the floodgates, and now all of a sudden whatever amount of current can flow through this circuit, whatever the circuit resistance limits the current to, then all of that will be able to flow. Up until that point, it won't. And this is kind of an interesting thing. We'll talk about the way that our meters can test a diode to see if it's any good or not. And this works for regular diodes and LEDs as well. When our meter does a resistance measurement, if it's just doing an ohms measurement, it only puts out about 0.3 of a volt, so 0.3 volts. That's not enough to push current past this margin, past this junction. Think of it like a wall. If I tried like a little bit to climb over a wall, I'm not going to climb over the wall. If I try a little bit harder, well, depending on how high that wall is, maybe I'll get over there. And if your meter has a diode check function, that's really all that's happening. It's just trying a little bit harder to pass current through whatever circuit, whatever component you're holding your test leads to. So when we put our meter onto that diode check function, it ramps the voltage up to 6 or 7/10 of a volt, 0.6 or 0.7, which is substantially more than 0.3. We've doubled our voltage. So that is enough to actually bias a regular diode. An LED, it's not enough to bias it, but it's enough to allow our meter to give us some information, which I will show you in a moment. So just another look at the same thing. Diode is a component with P and N-type materials. So, right, we're just beating a dead horse at this point. Here is my forward biased diode. I've got a battery with 12 volts, which is more than enough to bias this and allow it to flow. Obviously, I would need some sort of a resistor or a load in this circuit to limit current flow, because right now this is just set up to create a short circuit. So I'd burn up my diode, maybe a wire, maybe the battery would cook itself or explode or something fun like that. So the point they're trying to make is just illustrating the diode itself, forward biased. So it's in the correct orientation to allow current to flow. When it is reverse biased, the interesting thing that happens is, so my N-type material that has those extra electrons, they're drawn away from their Romeo. We've got, I don't know, some hunk over here flexing, I don't know, Dwayne The Rock Johnson or something, I don't know, just going for somebody. So some young stud standing over here that's attracting the electrons towards it, because unsimilar or dislike charges will attract one another. And the same thing's true over here. I've got a bunch of free electrons on the negative side of my battery, and those are definitely attracted to the holes that were created in my P-type material. So Romeo and Juliet being drawn away, they're distracted by other young love. And this is going to be an orientation that does not allow current to flow, because the voltage will never increase on my margin and never start that floodgate type situation. When we go to test our diode, we can test it with our diode check function. So you're seeing that here. It's illustrating diode check. One orientation, when we have it reverse biased, we should see OL, which means outside limits, and that just, or over limit, and that just means infinity. Basically, it's more than the meter can display, and the meter can display millions of ohms of resistance, so that's a lot. Here, we're seeing a very low number, 0.516. This number here is the actual voltage at which it is needed to start that current flow. So if I put 0.4 volts to this, no current will flow through it, or if any does, because if you get into some of the nitty-gritty stuff like micro, so millionths of an amp will flow through these when they're not biased, but like, what's that going to do? So this is wanting 0.5 of a volt to start that flow. So at 0.4, nothing will happen. At 0.5, then all of a sudden, wow, all this current's flowing, and it'll only be limited by the circuit. So if I have a 20 amp allowable current through this because of my resistance, well, then 20 amps will start to flow like that. So you can think of this kind of like an on-off switch, or zeros and ones. Here is me with my meter. And this is in the lab. You'll see an image of this. I have my meter on to the diode check function, because you can see an image of a diode here. And it's nice that they display the volts after this. I think that that's important, because this is what this is telling me is not that I have 0.6 of an ohm of resistance. It's saying 0.6 of a volt is what you need to get this diode to forward bias and flow. If I flip it around, it says OL, and you'll see this when you do the lab, and the only way I'm going to get it to allow me to flow in that reverse bias on a normal diode is to melt the diode and ruin it. So at that point, it's either going to be open, or if I get lucky, it'll melt and fuse itself together, and then I'll be able to pass current through it both ways, just like it was a wire. What do we use these diodes for? The way we know that they're used so far was in our charging system. They were part of our rectifier that turned AC current from our stator into DC current. This is incredibly important that we're able to turn AC current into DC current because our battery can only charge with DC. If I try to charge my battery with AC, I'm flowing one way and then the other, and then flowing one way and then the other. So I give it a little bit of current and then I take the same amount away. Well, that, math, right? That's not going to charge. With DC, I'm flowing the same direction all the time. I got a pipeline of electrons that are just going. And that way I can actually stuff them all into my battery and charge that up. The other reason why DC voltage is very important is because computers require DC voltage to work. They need a consistent voltage so that those ones and zeros mean something. If I flip my current back and forth, or my voltage goes positive and negative, I'm just going to make ones and zeros just because it's hooked up to AC voltage, so it's not going to do me much good, and AC is likely to fry the delicate circuits on a circuit board. This is why all of our computer chargers have a little box built into them to turn the AC current from the wall into DC to charge the battery on the computer, and also to power up the computer while that battery is charging, or helping the battery with running the computer, and it has to be DC current. Here is AC current that's not been rectified. When I rectify it with a diode and turn it into DC, it'll allow current to flow one way, and this is all showing current flowing in one direction. It's changing its pressure. This is the voltage. So at first I'm not pushing too hard, and then I'm pushing real hard where it peaks, and then I start to push less hard, right? So if I made a visual illustration or demonstration of this, it would be I'm pushing but not that hard, really hard, not that hard, right? Maybe I'll start over here because cameras. Not that hard, really hard, not that hard. And what's being rectified by the diode is it's not allowing the current to flow back the opposite way. It's always going this way, even though it's like a little bit, a lot, a little bit, still headed in the same direction, okay? And the way that we get around this voltage fluctuation that would happen is by lining up 3 circuits from my stator and having enough diodes to control that. So I just overlap them, so I get that little bit of AC ripple, if you remember back. And here we are, 3 circuits overlapped, rectified, and then this little bit of AC ripple there, which is much, much less extreme than what we would see here. This would be like headlights flashing and computers clicking and relays turning on and off and all kinds of stuff like that. Kind of like if we had a high resistance in the circuit off the battery, or a dead battery. Go to turn stuff on, stuff's flickering, flashing, lights are dim, things are moving slow or not at all. Another type of diode is an LED. So this is just a light emitting diode, and when we put current through a regular diode, like what we've been talking about up to this point, the current, we lose a little bit of our current flow, tiny little bit, to heat. And a lot of times it's pretty imperceptible. You could grab a hold of one and never really know it. An LED, when we are when we're passing current through an LED, some of that electrical energy gets turned on into light energy, so turned into photons, and then the semiconductor material lights up because it's fancy, and we get light out of it. And this requires way less current flowing than a light bulb, because a light bulb turns electrical energy into heat energy that heats up the filament to the point that it's glowing, and then that produces light. So we waste a lot of the energy with heat. We just skip the middleman and go straight to light energy, LED. There's our diagram. looks just like a diode, but they're showing the little arrows. These are photons, so light coming off of our LED in that case. And these forward and reverse bias the same way as well. We won't be dealing with these types of diodes on our lab. This is a Zener diode. Your kit comes with one, but I played around with it, and the thing's so wimpy that you can overcome the reverse bias no problem. So that being said, a Zener diode works like a regular diode, where it allows current to flow in one direction if we raise our voltage up to the point at which we can jump over that margin. But it'll also allow current to flow in the opposite direction if it's met with a big enough voltage. So let's say it takes half a volt to flow the normal way. It might take 40 volts to flow the opposite way. It's like all big and tough. Yeah, you can't get this way. I'm a diode. I'm stopping you. And then all of a sudden, a really big, tough voltage shows up. Like, oh, sir, right this way. You can come on through. And these Zener diodes are used for many, many different applications. What we'll see is often that they're used, and like they won't even show this in the diagram, but nonetheless, what they're being used for is circuit protection, fuel injector. Hey, look, I've got a coil of wire making an electromagnetic field that opens up the pintle against spring pressure, allows fuel to flow, shuts off. Magnetism collapses and creates thousands of volts, trying to flow current back towards the computer. This is a transistor, which we'll deal with next week, a little solid state switch. This cannot handle thousands of volts. It's amazing that it can even handle the 12 volts that would be in this system, and it really can't, because look, 12 volts comes in, it's dropped, and there should be no voltage here at the end. These tend to be fairly robust because there's at least some kind of current flowing through them, and they're worried about circuit issues. But if you have a bad enough short to power on this ground side, it'll eat this up with 12 or 14 volts after some time, whittle away at it. So that being said, 2,000 volts flowing back towards it is more than enough to lunch this thing. Just going to gobble it right up. So this Zener diode is there to try to make things easier. This current does not want to flow this way through my transistor when it's turned off. It has lots of resistance in it. So if this at 35 volts goes, I surrender, and allows voltage past it, we can just drop the voltage off that resistor built into the computer and save ourselves a lot of cost and heartache. And that is the end of our show. Please make sure that you follow the notes on the lab, and I think you'll get a much better idea of how these diodes work, and especially how LEDs work as you work your way through. Thank you.